Welcome to Study Loop.
This is the answer to Chapter 13, problem number 21 from the Smith Organic Chemistry textbook. And in this problem, we're given two molecules. Well, we're given two sets of information about molecules, and we're asked to determine a structure for each of these molecules based on the information that we've been given. And to me, this is where organic chemistry really gets fun and interesting because it's really just an exercise in problem solving, which I like a lot. So hopefully you do too. So basically, we just need to use the information that we've been given and determine different things about the molecules based on that information, and then we can propose a valid structure. So for A, we're told first that A is a hydrocarbon. So this is good because it tells us that there is only carbon and hydrogen in this molecule. So then we're given an M to Z, a molecular ion of 68. So our formula is going to have to equal 68. And again, we have only carbon and hydrogen here. And so I think that the way to approach this is probably just to think, okay, well, we only have carbon and hydrogen. So how many carbons can an M to Z of 68 accommodate? And so the answer is 5. 5 carbons will account for 60 of that 68. And so we can then fill in what's left with 8 hydrogens. And so if we then do a hydrogen deficiency index based off of that C5H8, so it's going to be 2 times the number of carbons plus 2 minus the number of hydrogens, all of that over 2. So we get a hydrogen deficiency index of 2. And so if this is indeed our correct molecular formula, then we're going to have 2 pi bonds to account for, or 2 rings, or a pi bond and a ring. Okay, and so we can now look at the IR data and see what that is going to tell us. So our first piece of IR data is a peak at 3310 wave number. And so that is going to correspond to an sp hybridized carbon bound to a hydrogen. So we have a CsPH bond. So that tells me that we probably have a triple bond, a carbon-carbon triple bond in this molecule. And that would be good because that by itself would account for the 2 degrees of unsaturation that we determined when we did the hydrogen deficiency index. So, that's great. So then we have our next peak at 3,000 to 2850. So by now, hopefully, you have it committed to memory that is going to be a CsP3 hybridized carbon bound to a hydrogen. And so lastly, we have a peak at 2120. And that peak at 2120 is also great because it confirms the presence of this triple bond. So we have a carbon-carbon triple bond. Right. Okay. So that carbon-carbon triple bond taken in conjunction with the peak at 3310, which was an sp hybridized carbon bound to a hydrogen, further confirms the presence of a carbon-carbon triple bond in this molecule. And so given all of those pieces of information, I think the easiest way to fulfill all of that is to say, okay, so here is our carbon-carbon triple bond. We'll make it a terminal one so that the carbon has a hydrogen bound to it. And again, this piece of information tells us that it has to be a terminal triple bond. And so then we can just make the rest of the molecule linear. Why not? It's simple enough. So CH2, CH2, and that's 1, 2, 3, 4 carbons, and then CH3. And so we can quickly count. So there's 5 carbons and 1, 3, 5, 8. So 8 hydrogens. So it fits with our molecular ion. It fits with our pieces of IR data. And it is a hydrocarbon, as the problem stipulates. So I think that's a good answer to A. So then looking at B, we can do exactly the same thing. So we'll follow the same steps in the same order here. So CH and O in this molecule, okay, so it's not a hydrocarbon. It's an alcohol or a ketone or an ether, something with an oxygen in it. So we have an M to Z of 60 here. And so this time it's not as straightforward as just saying, how many how many carbons could this accommodate? Because we could say it's 5 carbons, and that would get us exactly 60. But we have hydrogen and oxygen as well. So 4 carbons would be 48, but oxygen is 16, so 4 carbons isn't going to work either, because we know we have at least 1 oxygen, and 48 plus 16 is 64, and that's too much. So let's go with 3 carbons to start. So C3, and then if we assume that we have only 1 oxygen, so 3 carbons is going to be 36. An oxygen is going to be another 16, so that'll get us to 52. So that leaves room for 8 hydrogens. So our formula could be C3H8O. And I'm going to go ahead and just assume that that's the correct formula, and do the HDI. So again, HDI is going to be 2 times the number of carbons plus 2 minus the number of hydrogens, all of that over 2. And it ends up being 8 minus 8 over 2, so 0 over 2, so 0. So no unsaturation here. So that's good. We don't have any double bonds. We don't have any rings. So we can look now at our IR data. And so this first piece of IR data, this broad peak at 3600 to 3200, is going to be from an OH stretch. So that tells me that we have an alcohol here. And then our other piece of IR data is just CsP3 hybridized carbon bound to hydrogen. So CsP3H. So this is a pretty straightforward molecule then. We have some carbons bound to each other and to hydrogens, and we have an alcohol. And so the easiest way to draw that is just as a straight propanol, CH3, CH2, CH2OH. Okay, and so if we want to count, we have 3 carbons, we have 8 hydrogens, and we have 1 oxygen. So that fits our formula. So it fits our molecular ion that we were given. And we have bonds that would account for the IR peaks that we have, and no other bonds that would account for peaks that we haven't been given. And so I think that this is a good structure for an answer to part B. And so that's the way to approach this problem. We just need to individually consider each piece of information that we've been given and use whatever it's telling us, and then take all of those pieces of information in aggregate to determine a formula. And so I think the way to do it is to use, they tell us what type of molecule it is, so start there, then look at the molecular ion and try to determine a formula. Having determined a good formula, calculate an HDI, and then use the IR, each piece individually, to determine what type of bond that IR peak is describing, and then put all of that together. And so that's the answer to chapter 13, problem number 21.